to the Santa Barbara Hackerspace Tech Talk. Nick Winters is going to give a talk about introduction to PLC for Arduino people. Take it away, Nick.
Hi, everybody. So I got into, well, I'm a professional software developer. I've been doing software development for 19 years now. And lately I've been getting into more industrial automation with PLC programming. And it's been remarkable how much the concepts for Arduino apply, but with different names for PLC programming. So that's what I'm going to try and show you today. First, I got to click on my slides. So the slides and code and video will be available online on our GitHub and YouTube channel. And I'm going to start with a quick introduction to Arduino. So there's a huge mess of Arduino boards that you can search for. They all have a bunch of common elements that are not universal on every single one of them, but common across many of them. You program them in the Arduino IDE software. They often have stackable header connections that you can plug additional boards onto them, and often they have breakout connectors. So for example, here on the side of this new Arduino Uno R4, there's a connector here you can plug sensors into to communicate with them. The expansion headers, you plug boards in, they're called Arduino shields, and then for other dev boards that are called different things. I have a handful of examples here. In the top, we have a 7-segment display. We've got a joystick. We've got an array of lights. We've got Ethernet. We've got NFC card reading or writing. So I'm actually going to start off with some simple Arduino demos. Let me start off with the board I'm going to demo. So this is a STM32 Nucleo development board. It's about $13. I'll show you why it's neat later, but effectively it's like the Arduinos you're used to, but it has an STM32 chip. So I'm going to start with just a simple blink the lights. We set up the built-in LED on the board as an output, and we turn it high for 500 milliseconds of delay, and then we turn it low and then delay for 500 milliseconds. It'll take some to get the lighting. This is frustrating. The LED is over here, but it's difficult to see with the lighting. There we go. Thank you. So that's our super simple example. Let's load up something else. Do I have it already loaded? Nope. So is this straightforward to everybody here? Oh, yeah, sorry, something I forgot to mention. If you have a question, raise your hand and Dan will bring you a microphone. So this example reads the status of the user button, which is on this board a blue button, the second button here, right there, and copies that to the LED. So when I press the button down, the LED's on, and when I release it, it turns off. Super simple. Let's go through the code for that. So we set up the built-in LED as an output. The user button, we use the input pull-up. So the logic actually is going to be inverted. When you press the button, it will short the pin to ground. And we also have a counter that we initialize to 0 and we print out over serial. So I showed you the button working. and you set the correct baud rate. Is the text suitable for you guys to read on that? Okay, thank you. So we have a number going up, and another cool Arduino feature is if you have multiple numbers, you can plot them, and they go up and to the right, like everyone wants, in this case. So, super simple demo. I want to show you the expansion connector that the board from my slides has. So on this board, I plugged in these headers going to this connector. And you can buy boards with these connectors on it that you plug in series. And so let me show you my demo with these. So this is using I2C or I2C. So what this demo does, I have a I2C OLED display and an I2C ambient light sensor, and it prints on the OLED display the value seen on the light sensor. I'm not going to go over the code for this. I just wanted to show you that it's there and it works. I keep hitting the annoying feedback shortcut. So the numbers are almost visible. And then as the light decreases, the numbers go down, and as it increases, they go up. But I wanted to show you this expansion approach where you can plug multiple things onto the same signal wires for some PLC stuff we'll get to in a bit. This is fun. So Walkwe is an online way that you can test your Arduino sketches. Here's a super simple demo. We have a Arduino Uno. We've got two buttons that pull, one of them pulls pin 4 and one of them pulls pin 2 to ground. We configure them both as pull-ups. Again, like the second demo I showed you, we configure the LED as an output, and when you press the green button, the LED right here turns on, and when you press the red button, it turns off. Another cool thing about Walkwe is these buttons are associated with keyboard keys. So 1 is the green button, and 0 is the red button. So you can test what happens when you press both of them at once, and so on. Another cool thing that is really special about Walkwe is their beta debugging feature, which is really incredible when you can use it, which is way better than debugging via serial printing. You can set line breakpoints and then do the serial debugging, and it'll actually spin up GDB in your browser, reach your breakpoint, and you can check the status of all of the pins and the status of all the globals, and if I had locals, they would show up here as well. Which is really incredible, because setting this up with Arduino and then the $100 debug interface, and then you can't use the Arduino IDE for most boards for this, it's a hassle. However, the reason I chose this board is because you actually can do that in Arduino. Let's go to a slightly simpler sample. So in my hello sample, I can set a breakpoint. And because I'm using this Nucleo board, which has the debug interface on this portion of the board, when you set this up properly in Arduino, to use the programmer debug interface and to use the I'm not reading the menu quickly enough. To debug and to use the debugger, wherever that option is, you can upload and have breakpoints, and then use this new debug button in the Arduino to debugger, or Arduino to IDE. We are stopped at a breakpoint. So I don't have any locals. Do I? Yeah, I do. So the button status is 0. So continue will continue executing. The currently stopped line is this line that the text cursor is on, which is really low contrast to display. So I'm going to switch to the high contrast theme to make that more obvious. So this digital write line is the line we are about to execute. I can do a single step and it will execute that one line. I can do a step into, which won't do anything on this line, but on the next line we'll step into the code on that line. So we're inside of the definition of the prints. Step out steps back out of a function. So I can step out of loop and I will be wherever loop is called. And then continue, this continue right here will continue executing until it reaches my next breakpoint. So if I hold the button down and press continue, now button status right here changed to a 1 because I was holding the button down. So when you stop debugging, it disconnects. And I'm going to switch back to the normal dark theme because that's the end of this demo. That's pretty cool that you can do that in Arduino now. Previously, you had to do that outside of Arduino in Atmel Studio or Visual Studio or Platform.io or Microchip Studio or MPLab or some other complicated IDE. Changing gears entirely. I hope you all have seen a relay before. I'm going to try and explain a relay. This, by the way, is an awesome set of photos from the book Open Circuits, where they cut open circuit components and actuators and so on, and take really nice photos of what's on the inside. The relay inside isn't as difficult to get into as like them sanding a circuit board at diagonal. But anyway, that's a cool book. So this particular relay, you can see the big coil, solenoid coil here, and then it pulls down this metal bar and it hinges, and then all of these 4 contacts switch from being connected to the leaf to one side, from the leaf to the other side. So schematically, relay symbols look like this, or can be drawn like this. I'll show you more in a bit. So a simple relay would just have a single normally open contact and a relay coil, but you can have a contact that toggles between normally closed, the C and B, and normally open, or multiple such contacts, or this big relay would turn into this kind of monstrosity. So let's show you a simple start and stop circuit. So say we're starting and stopping a motor and we build it out of a relay. The additional contact would control, you would use one contact in this relay here to latch your circuit on. So sorry, this is an example where we have one button that turns a motor on and a separate button that turns it off. So we have a normally opened push button for starting and a normally closed push button for stopping. We have 120 volt mains coming in one side, and eventually that will power the coil and latch it on, and then our mains neutral on the other side. So when we press the start button, that powers this circuit and powers the coil, and then when the coil toggles the contact, it will then go back and power around the outside back to the middle here to bypass the start button, so it will latch itself on, and then the stop button will turn it off. if we are drawing a lot of these, it makes sense to move the display of the relay coil and the contacts somewhere else in the schematic, because we're going to have, even for the previous example, you're going to have contacts for this powers my motor, and then this is my contact for latching the on, off, start, stop button relay on. So the relay, in this case, coil is just drawn as a circle, and the relay normally open contact is drawn as these two bars. Continuing further, when you turn that kind of relay logic for your industrial automation into ladder logic for software, it's the same thing, except your start and stop switches turn into contacts. So we have a question, by the way.
So in this diagram,
Yeah.
how would you define a relay versus like a capacitor? Is it just distance between the two elements, or are these two entirely different schematics?
I'm transitioning from a relay, from a electrical schematic to a logic schematic.
Got it. Okay.
So it is very much the same shape, but the spacing between the two lines is a bit further apart on a relay contact than it is a capacitor.
Got it. Thank you.
But yeah, if you're looking at old pinball machines, their contacts are drawn this way, because you'll do electrical, as you'll see later, you'll do electrical schematics using the logic symbols. So in this case, my start button turned into a normally open contact, and my stop button turned into a normally closed contact, is what the symbol is here. And my call out for which side is line and which side is neutral of the feed into this disappeared, because it's implied, as you'll see when things get more complicated, it just continues drawing longer. So I'm going to demo a PLC, and we're not going to get back to Arduino for a bit. Here's my wiring diagram for the PLC I'm going to show you. So we have, yeah.
Could you like sort of give a background as to what a PLC is and why you would use it,
Uh,
or why you need to use it?
So, thank you. The history is that industrial automation was originally done with relay logic. So you would have a panel with 1 million relays, and your relays would have a mix of normally open and normally closed contacts, or even your pinball machines, if you've watched the Technology Connections video, would have a giant combination of contacts and drum rollers to increment things. And so what I'm working towards is, with the examples here, is that PLCs turned those physical relay contacts into a software system. So previously they would do automation for, you've got a punch press that increments your feed or increments a table or does something else. It performs some sequence of actions wired from relays. And at the most simple level, your programming would be just a single relay like this, but in practice it would be hundreds and thousands of relays. Dan, we got a question behind you. For industrial automation, you would have a whole number of relays actuating different solenoids that would actuate air cylinders or whatever else, driven by sensors in your system and so on. So your PLC allows you to simplify your control cabinet and make it more flexible as your system gets larger, and eliminate a whole lot of parts in your control cabinet that used to be individual components. As we'll see later, in your PLC, you can have like a virtual component that'll do like a time delay or something else that used to be a physical box that you plugged in. You'll still have physical boxes for like thermal overloads or sensors and so on, but having your schematic become simplified in this way, and then so much more flexible. You can have like a time limit for how much the on time is, or calendar or data logging, and your electrical schematic for your control panel remains the same. So that's why PLCs are used in industry. And the reason they're programmed with ladder logic in America, at least, is because the transition into PLC programming typically doesn't come from the software side. It comes from the electrical side. So you have people familiar with the like power electrical codes and not blowing up wires and catching wires on fire, getting into PLC programming. So the logic from relay logic may make more sense to them. It's unfortunately not the background that I come at it, and if you're familiar with Arduino, it's probably not the background you come at it either. So we'll show some more examples of that later. Does that answer your question? Awesome. So yeah, this is a tremendously simple example of a simple PLC with two inputs. Again, we have a normally open push button and a normally closed push button that feed into inputs on the PLC. And then we have two lamps. One's orange and one is green. I'm sorry if you're colorblind, that's what I bought. And then the PLC is powered by 24 volts and 0 volts, and then there's another couple other connections that make the inputs in the PLC work. So let's walk through this. So we have our 24 volt power supply. I have my 24 volt power is this blue set of terminals and blue wires, but also my other blue wires are either 24 volts or not, depending on the outputs or the switches. Here's the CPU, and then here's all of the IOs that we saw in the previous schematic. Can I put this slide? Yeah. And again, I have a white button, normally open, a red button, normally closed, an orange lamp, and a green lamp. Let's do a demo. Actually, a few demos. So connect. It would help if I plugged in USB. Okay, so this is a super simple example. So we just have the white normally open button, open contact directly to the output. I gotta click a few more times. I'll explain those dialogues later. And we have a red normally closed button connected directly to the output. So this lit up because the normally closed button that I have wired in is powering the input. And then the input goes through the virtual normally open contact and then powers the output. So as you can see, the green light is on. When I press the red button, that'll toggle the green light off, and will also toggle off lighting up the corresponding parts of the program. So when you're debugging a ladder logic PLC program, you can see the status of the inputs and outputs live as you're running it. So let's load up the start and stop example. It's slightly more complicated. So it's saying the program saved in the PLC is a different project name than the one I'm trying to overwrite. And then when I did that upload, it stopped it running and is asking me to start it running again. This PLC and many others has a little switch on the side of it that can stop it running and start it running. So we have, when I press the white button, it powers the output, and then when the output is powered, it continues to power the output. And then when I press the red button, it turns it off. Does that make sense to everyone? So the way this is being executed is the rungs, this whole line here is a rung, is being evaluated from top down in software in the PLC. So you can have combinations of things that wouldn't make sense in an electrical schematic, like assigning to the same coil more than once, or having a output that, like, when triggered, turns a coil on in one direction, but it isn't a continuous thing, it just latches it on, that don't exist as electrical components. So for example, down here, there are rising and falling edge detecting contacts that can be in your ladder rung. And you can draw lines between things and insert additional circuit components. Let me check if there's another demo I wanted to show you here. No, I think that's it on this demo. So yeah, this is what I just showed you with the ladder logic for the start-stop. But let's go back to Arduino, because Arduino is not at all like this. So let's talk about this weird Arduino. So Arduino partnered with a group called Finder that has like DIN rail mounted relays to build a Arduino with relays. So I know this is kind of small, but this little thing has a 12 to 24 volt power input. It has 8 0 to 10 volt analog inputs, and then it has 4 normally open relay contacts, which I believe are 10 amps at 250 volts AC. Yes. So you could like run a small motor or turn on a moderately sized light with each of these, and they're relay contacts. So I have one, let me show you. So like my previous demo, I have a red and white button, orange lamp, green lamp. Going through the components on here real quick, I have a 12 volt power supply, a 24 volt power supply, the Arduino itself, and then a couple relays. Let me show you the schematic. So I have 12 volts going through my push buttons, same as before. I have it feeding into relays, but in kind of a relay switches in kind of a weird direction to drive a DC motor. So this way, depending on which of these two relays, forward or reverse, get powered, the gear motor will go one direction or the other direction. And then I have the 24 volt power supply powers through the relays in the Opta, either the 2 lamps or the 2 relays. These relays are actually pretty cool. I wish I had... Now let's pull one out and show you. They got a little window so you can see inside, and that little orange bar you can see through the small window here. And then there's a little green button that you can use to actuate the relay that actually moves the contacts mechanically and not electrically. And then this goes into a plug socket. And so I can actuate the relays manually, which might be familiar to you if you've worked with air solenoids also. So let's do a demo with the Opta with the Arduino IDE. This should be very familiar to what you guys have seen previously. So if you remember the diagram, there's 8 analog inputs. I'm setting those up, and then I'm printing the first 2 of them because I only have things connected to the first 2 over serial. Yeah, I wanted to put a slider on there. So I'm going to bring up the serial monitor, and one of the inputs, the red button one, is high and goes low when I press the button, and the other one is low, goes high. So it's an Arduino, but it's in a funny shape, and it doesn't have shield headers, and I can't plug quick stuff into it. Why? Because of the relays. So this is a straightforward demo that increments through the 4 different outputs, and it turns them all off, and then turns one of them on in sequence. The relays also have a little indicator light for when they're powered. This is going to get a bit annoying, so I'm going to upload the previous one while I go back to the slides. So yeah, the Opta with the Arduino IDE is an Arduino. You can pin mode and analog read and analog write, and there's libraries for the Ethernet on here, or Wi-Fi or Bluetooth or whatever. It's not very exciting. We got a question.
Question from the interwebs. Can you PWM things with relays, or is that inadvisable?
You absolutely cannot. You can turn relays on and off, but the frequency that PWM would turn an output on and off would destroy a relay. It would arc the contacts. When you have current going through and you open the contact, it will arc a little bit, and that will wear out the contacts over time. And so at the speed that PWM turns stuff on and off, you would definitely destroy the relay outputs. I'm going to mention later, although I don't have a slide for it, there are ways to do PWM outputs, but not with relays. We got another question.
As sort of a follow-up to that, though, could you still do the digital PWM output, but just use the relay as effectively just a contactor or switch? So send the PWM.
What I'm saying is the physical relay doesn't actuate fast enough
Right,
to do...
like the operate and release time of the relay is not compatible with the frequency of the PWM signal, but can you still just, yeah, I suppose just use it to connect the line in or whatever you want to run your motor, and then, you know, also kind of power it then with the logic controller? I
don't know if I'm answering the same question you asked. So the relays here are incredibly useful because you could switch mains powered lamps or motors or whatever else. If you want to switch something at a high frequency and like vary its intensity like you would with PWM, then a relay output is the wrong choice.
Yeah.
There are other outputs that I'll talk to later that allow you to do that. And unfortunately, with this Arduino PLC, that's not a straightforward thing to include. So I'll also talk about how you can expand this for more input-output options or numbers.
Right. Yeah, I think I was misunderstanding. It's like if your PLC can do the PWM control of it, you wouldn't need the relay. Like
you need
just
some
do it. You
other.
would just do it with the controller.
Yeah.
You know,
If
you would just
you
have a
want
transistor or something.
Yeah, if you want a PWM output, you need the correct kind of output for your PLC. And I'll talk later about how to get that.
Thank you.
So yeah, the reason you might choose the Arduino Opta, however, is to be able to use the Arduino PLC IDE. Which I'm going to start off with looking familiar to what you've seen before. We have our ladder logic, and it'll start and stop. I want to mention a thing real quick. When you first connect to an Opta, you need to go to this resources page and click on the Opta to load it up. And then you'll download a program into the Opta. So when you're switching between the Arduino IDE and the PLC IDE, there's like 2 programs that you need to load into the Opta for the PLC IDE. The first one you do here, that's not something I'm used to. And then the very, very first time that you do that, you need to activate the PLC license for the Opta. So when you buy the Arduino Opta, there's a PLC license for that particular hardware, and it's included in the Opta, but you have to pay extra for it on other boards. It's not a license for your development software, it's for that physical device. So yeah, it's gonna take a bit to upload. We have any questions? No? Go for it.
Is there digital I/O on the Arduino PLC?
Not on this one. There is on another one. So the only there are no pins that you can convert between inputs and outputs. There's only inputs and relay outputs, and then the relay outputs are relay outputs. They're neither. Sorry, I'm having to deal with demo gods. Yeah, so the Opta is relatively affordable. It's $140 or $160, I believe, is the one that I have, or $200 if you get the one with Wi-Fi and Bluetooth. The fancier board, which as long as I'm waiting for this to talk about, the Potentia machine controller has no relays, but it has way more inputs and outputs of different types, and it's about $400, including the PLC license. It's like $370 and then $20 or so for the PLC license. You can program that in the same software, and it has digital IOs and inputs and temperature inputs and CAN bus and a whole bunch of other cool stuff. Okay, so I have downloaded a thing onto here, but my program isn't on here yet. So I need to connect and then click download again. So it should say connected over here. That's annoying. Demos are great. Online setup communication, so we're using Modbus over COM4. So one notable thing, I'll explain Modbus more in a bit, is that we don't need to be connecting via USB. I could be connecting via Ethernet into the switch I have over here to connect to this Opta or to reprogram the click or other PLCs when they're done this way. So that's the reason I needed to upload and then upload again. Darn, the demo gods are not behaving with me. This is tremendously irritating. There we go. Okay, so as we can see down here, we're connected and no code is uploaded, so it's uploading the code. I get to do that again. It's great. When you get it, when you're not switching demos, it's a much smoother process, as you will see. But because I'm going to keep switching demo programs, you're going to spend a lot of time watching me upload code. So I would like to explain this. So retain and non-retain variables will be sent means it is overwriting the saved state inside of the PLC. So one of the features of commercial PLCs is that your variables can be persisted through power cycles. So it can have like an hours counter or whatever else and remember the state it was in when it was powered off. So that would be a retain or retentive variable. I'm not going to show you how to set that up today, but I wanted to mention it to you because it's an option that you should look for when you're programming. I hope I don't have to give up on this. I have a lot of demos to show you. You're right. I'm sorry, Dan, I'm debating whether I want to jump ahead and reorder my slides to answer what is Modbus before the PLC demos I wanted to show you. I might just do that. Let me... Dan, you're throwing off my whole thing. You're right. I mean, I brought a couple more. Okay, so I am completely reshuffling things. So, yeah. Let's talk about PLC expansion. Let's forget about programming and talk about inputs and outputs. So if I were back to talking about the click and responding to his question about how do I have a output that I turn on and off at a high frequency to control a heater or whatever, you buy the output or input module that works for the particular thing that you're talking about, and you plug it into the side of your PLC. That will soon be an option for the Opta. They've announced 3 new Opta expansions that are the same physically that plug into the side of the Opta. There's a little connector that you plug into the side that then the next one plugs into. One of those brings in temperature sensors instead of the analog sensors. One of them has an output that isn't relays. I forget what it is. And if you're looking at another PLC like the Click PLC, there's a huge variety of input and output modules there. I have a screenshot here of a couple of them. And there's also the communication interfaces on the PLC itself that you can use to expand your options by networking to another device. So I was just describing I/O modules. Let's go over a list of some variety of input and then next output modules. So digital 24-volt DC syncing or sourcing. I'll explain that in a bit. Or AC. So there's a little AC light inside that triggers a transistor inside. Or analog inputs, 0 to 10 volts AC, or 10 volts DC. There's that typo I missed. So the Opta, for example, has 0 to 10 volt DC inputs. So I could connect a slide potentiometer, or I could buy a sensor that outputs 0 to 10 volts DC. I could have a VFD that outputs the current speed is 0 to 10 volts, or a temperature sensor, or a current clamp, or I have a laser distance sensor at work that outputs a distance in 0 to 10 volts. In industry, 4 to 20 milliamps is also slightly preferred, but more expensive. And so you would use 4 to 20 milliamps of a current input to be able to distinguish the sensor being disconnected from its minimum value. And also, as your cable length gets longer, the milliamps doesn't get offset by the resistance of the cable. There's a controller in your sensor that will keep the current the same as the length of the cable gets longer and your resistance increases. So if you care about the particular value, 4 to 20 milliamp analog input is what you would prefer. You can buy devices that can do both 4 to 20 milliamps or 0 to 10 volt DC inputs. There's different temperature sensor inputs, and there's also high-speed inputs that can do things like count the number of pulses of an encoder going by, or the position and direction of an encoder. We have a question?
Yes, we do. From the interwebs, do the AC inputs require AC, or did they respond to an RMS value?
The way they're implemented is the same as the DC inputs with optocoupler inside. So there's a little light on each input physically inside of the PLC. And if you reach the voltage it's looking for, it will light up and then signal that down inside of the PLC. So a 24 volts AC input might not turn on at 24 volts DC, but there's a voltage it will. Outputs have much the same variety. Digital outputs, either sourcing or syncing. I'll again talk about that in a bit. AC outputs that have, great, I'm blanking. What is the T word for switching AC? Triacs. Instead of transistors. Or relays. So relays, as you saw on the Opta. Or analog outputs, either 4 to 20 milliamps or 0 to 10 volts. So you might have an analog output on your PLC that you wire to your VFD, for example, to set its speed. Or you might have a high speed output that you use to output a motion path, which is actually the reason why I bought that particular Click PLC, is that it has high enough speed outputs that it could output step and direction or a quadrature position path for doing a motion on a servo or a stepper driver or whatever. Or pulse frequency. So instead of doing PWM as a duty cycle, you change the frequency of the pulses and not the width of them. Syncing and sourcing is something that you should be familiar with if you've hooked up an LED to an Arduino. It works much the same way, where on the left here we have a sourcing input versus a syncing input. And this is pretty similar to having a input pull up and your switch pulls the line to ground, or having an external pull up and your switch pulls the input high. We have a question?
Yes. Can you talk about wet and dry contacts? Seen those on PLCs before.
Nope. I think that's too deep to go into for this talk. And then for the outputs, the digital outputs on a PLC, you might have a sourcing output where the 24-volt power gets switched to the positive side of your output, or it could get switched on the negative side. So 24 volts goes through your load, your lamp in this case, and the negative side gets switched to ground. When you're purchasing a PLC I/O module, you need to choose which one of these because it changes what kind of transistor is on the outputs. Whereas on the inputs, the optocouplers, these LEDs, they tend to wire them in both directions. So there's a pair of LEDs, one wired one direction, one wired the other direction. So you can wire the other side to a common wire. So your common wire would be either plus 24 or 0 volts. And then that group of inputs will all either be syncing inputs or sourcing inputs. Is that a question? Just scratching your head?
I don't know, maybe this is just an industry standard, but it almost seems like it's reversed, where syncing.
Just saying it to me sounds like you would sync to 0 volts, whereas sourcing would be you would complete the circuit from the input power of the 24 volt. Is there any? I mean, I guess what's the logic behind kind of being on the high or the low side of the element?
Are you asking, like, why would you choose to use a sourcing versus syncing input or output? Or are you asking why is it termed a sourcing?
Just why is it termed? And if there is no answer, then that's also reasonable.
You're thinking about the conventional current flow. I'm getting frustrated by my demo not loading. That is really annoying. Okay, so I'm gonna have to go through all my demos without showing them running. So going to the diagram, you're thinking about whether the current is going into your PLC or out of your PLC. And so that makes it a bit confusing where the terms switch around depending on if it's an input or output, but for the same kind of wiring. Yeah, I don't really have a good short way to explain it. Short way to have it be something that can help you remember it. You have to think about, like, the load is the device you're powering for the output, but it's the PLC itself for the input, which is why syncing and sourcing get switched around between the two of them. I don't know that that's a helpful way to understand it, but that's the way I think about it. One of the reasons I'm explaining sourcing and syncing outputs here, so like making such a big point of it, is because if you're connecting something else to your PLC, so in the motion case is the case that I am more familiar with, where you're wiring a stepper drive or a servo drive to the high-speed outputs on your PLC, you need to be aware of what kind of what direction those expect you to pull the pins to make them active. And when working with stepper drives, they expect their pins are being pulled up internally, and then your PLC will pull them to ground, which is not the way you would typically think about, like, I'm turning on a light, is by pulling the light to ground, which is why you need to be aware of them early enough in the process that you're buying the correct module for your PLC. So yeah, let's talk about the other stuff, connectivity. So the Arduino Opta that I purchased has, all of them have Ethernet. So the Ethernet jack is on this ledge here and not visible. And then the one I purchased has RS485 serial. So Ethernet, I hope you're all familiar enough with it. You plug it in, you get internet or talk to a thing or whatever. RS485 serial is conceptually similar to the other serials I expect you guys have worked with, like FTDI serial, a UART, or RS232 serial back from the dark ages. RS485 serial, the way the signaling works is a little bit different, so it's its own thing. But it's more noise immune because it works on a differential pair of two signals. So you can have a longer, like 10s or 50 feet run, maybe, probably be kind of marginal at that length, that you wouldn't do with an RS232 serial link. Built on top of that, on each of those, is a protocol called Modbus. So Modbus RTU is the Modbus protocol running on top of RS485 serial. Modbus TCP is the protocol running on top of Ethernet and IP. Question?
If you want to extend,
Don't be afraid of me either.
If you wanted to extend the length of the signal that you could send over wire, like 50, you said was kind of marginal. If
Yeah.
you wanted to go 100, what would you use? You'd use some sort of switch with a booster or something, or
No, I
you
would
just
use Ethernet instead.
just use a different type. Okay.
Yes. Which is 2 slides from now, but whatever. So if you're connecting devices with Modbus RTU, you connect the corresponding pins. So the center pin is ground, the pin on the left is A-, and the pin on the right is B+. And you connect A- to A- and B+ to B+. This is unlike a UART serial where you connect TX and RX. But part of the reason, or the helpful reason that's notable here, is that you can have a third device that you also connect A- to A-, and a third and B+ to B+, or fourth, or 20th. But we've seen this before. We've seen this with I2C, where you have ground and SDA and SCL, and you connect that across all of your devices. And we send messages with data in it through the devices down the chain, and we talk to them with an address in the device. So with Modbus, you tend to have smart enough devices that their addresses aren't fixed. You can reprogram them, but you're still limited by the number of devices that you can have on a single Modbus RTU RS485 chain of serial. And you're limited baud rate wise as your cable gets long enough by its capacitance, just like I2C. So you have server devices and client devices, much like you're familiar with I2C or that previous Arduino example. So the server is the one that is typically your device. So your like current clamp or your temperature sensor or your, I don't know what your sensor is, that sits around waiting for something to talk to it. And your client is the device that makes the requests repeatedly and either reads or writes or some combination of those. The commands to read or write have a function code. This is a screenshot from Wikipedia, and there's a number associated with that, which you'll set up when you're connecting to a device. To the upper examples here are dealing with inputs or coils that are a single bit, or more likely 16 bits for holding registers or reading and writing or whatever. Similar to how you'll read from an address in an I2C device. Yeah, much like I2C, you, I hope you like reading data sheets because you're going to be looking at a big table of addresses to find what you need. And let me walk you through what that looks like in the PLC IDE. Yeah, I wasn't able to get my demo running. Here's some code. Can I make that bigger? Oh boy. I hope you guys can understand that code. We're gonna explain code like this a little bit more later. These are the slides that I skipped, but I have a variable somewhere. It's named count, and I increment it every time this runs. So this is effectively my loop that you're used to from Arduino. The way that's configured here is under tasks fast, I have my main function, that's what we're in right now, in the fast loop, and then I could write a new program in here, and then drag that into my init, and then this is analogous to my setup function. So where is my count variable? So that's declared here in global shared. But it's also set up here in my status variables. So this is fun. So I have a signed 16-bit integer named count at Modbus address hex 6000. Also known as decimal address 24,576. So if this were working, I could bring up this software, QModmaster, and connect to my PLC and connect over TCP and do the function code. I'm going to cheat and look at my slides. I believe it's 6. 3. Read hold registers. I'm going to read a single one. And my start address in hex will be 6000. And if my code were uploaded there, then when I connect and then click the second button to run continuously, the count number would appear here in decimal. Where are my slides? I have a screenshot of that. I actually mixed up my demos. I was supposed to show you Ethernet second. So first I was supposed to show you Modbus RTU. So physically, I have a RS485 serial adapter that I can plug into those 3 pins on the thing. But it's the same demo. I go to QModmaster, I connect serial to COM14 at 380/400 with those, and then connect RTU with a particular slave address that is configured in the PLC IDE right here. And then I could read from the same address. I could similarly, instead of reading holding registers, do write single register or multiple registers and change that count variable in the PLC. So this is how in Modbus you would read or write from a PLC. This is perhaps a bit more clear if we're working with a sorry, I'm winging it. If we're working with the click. This is not the demo I wanted. There we go. So this rung, there is a clock in the click that pulses at 500 milliseconds. When it goes high, that triggers this math node that increments the register DH101. And when you bring up the address picker in the Click PLC, it's actually super helpful at understanding Modbus because you can display the Modbus addresses, and it will show you the 3 different function codes you could use to access this address and the address. So the addresses 40,000 and something are a different way of numbering the Modbus addresses, and what address were we looking at? DH101. I could similarly connect to the Click PLC over RS485 Modbus, which I haven't configured, or Ethernet Modbus TCP, and read that address from the Click PLC's memory. So that's how you would have your Opta talk to a Click or other brand of PLC, is you would figure out what addresses you've mapped the variables to, and the Click is a very basic PLC, so you manually decide where those variables are mapped. Whereas in the Opta or another fancier PLC, when you define the status variables, you can define their addresses here yourself. And it's not associated with where it is in memory. It is a number that you've chosen to map directly. When you connect from the Opta to another PLC, you do something similar. You will add a generic Modbus device and then add a function code. So we're going to read holding registers from some other device. And then inside of that, we specify the starting address that we're reading from, and we type in names for what we want to read those as in our program. So we're connecting to another device and then reading its registers into our program as variables, and then I can treat those variables as additional inputs or additional outputs or whatever. Additionally, the standard variable size in Modbus, either Modbus, is 16 bits wide. So when you want something larger like a 32-bit integer or 32-bit floating point, you will use sequential addresses. So a 32-bit floating point will be 2 addresses, or a 64-bit floating point will be 4 addresses. And there's some compatibility issues there with getting the addresses incremented in the right order to go back into a number that make that kind of thing frustrating. So if you're trying to be compatible with other devices, that can get in your way. But if you're staying in the same family, they all talk in the same byte order, just like network byte order. What is my next slide on this? So I've talked Modbus. Modbus Ethernet is super easy to wire. You just plug everything into a switch, and you give, when you're addressing Modbus TCP devices, you're addressing them by their IP address. So you give them a static IP address, and you make those not overlap with each other. So you can have hundreds or thousands of devices, although you're limited by CPU time for how many you can talk to at once, but you can have a huge number communicating with each other. Additionally, having your device act as a Modbus server is the way industrial HMIs are presently done, or the old way they're done. So you would define Modbus addresses in your PLC code, and then your HMI would read and write to those for showing buttons on screen or readouts or temperatures or whatever. With the did I break it? No? Okay. So with the Arduino PLC IDE, you actually do have a sketch with setup and loop. And this is where you set up the IP address of the Opta itself. What it seems like is happening here is that the sketch is running on one of the CPU cores, and the PLC code is running on the other CPU core. So that will allow you some ability to bring in Arduino libraries. Though on the Opta, which has a limited set of inputs, you can't connect I2C sensors, for example. So I've already explained to you that for a longer cable run or more devices, you'd prefer to use Modbus TCP. What if we wanted to talk to an Arduino? So it turns out you can run Modbus TCP or RTU on an Arduino. So let's see if that demo works for me today. This is a Arduino Mega. I have an Ethernet shield in the middle. The Mega is kind of marginal for this. It's a bit slow. An ARM core device would be better. And then on top I have a Danger Shield, which is whatever. It has a bunch of cool things to play with. It has a 7-segment run by a shift register. It has a buzzer. It's got 2 LEDs. It's got a light sensor. It's got a temperature sensor. That's this transistor-shaped package. It has 3 sliders. And just like I failed to show you previously with the Opta, because I can't get code uploaded to that, I can connect to this over Ethernet, and I can scan from address. Read multiple registers. Oh, yes. I'm going to show you the code in a second, but I'm just doing analog read and sending those to Modbus addresses for, this is only updating once a second, for these 3 sliders. So this is the second slider that goes from 0 to 1022 or so, and the 4th slider also goes from 0 to 1022 or so, just like you'd be used to from an Arduino. So this is modified from the Arduino sample. So we initialize the Ethernet server with our IP address 172.16.0.11, and we have a Modbus TCP server. This is a whole bunch of stuff for the lights and the pins on the Danger Shield, and then we set up the inputs and outputs. It starts up and will complain if it can't talk to the Ethernet shield, and then the loop waits for a device to connect. So let me disconnect and show you the serial output. This is the wrong board and the wrong serial put. I think it's that one. What baud rate did I set up? Okay. No, is it COM14? There we go. Scrolling through the code a bit. So in loop, if there's a client connected, it will then loop while it's connected and update the danger shield. And if not, it will play an animation. So my animation here is it just going around the outside of the 7 segment. So I want to bring up the serial console and show you it connecting. And so it should say new client, and then now it's showing a 0 here because I can write from the client into the danger shield. In addition to reading the values, if I change this from read holding registers to write multiple registers, I think it's that one. No, that's my buzzer. This one, 1. So now I have a 1 on the display, or 2. So I can both read and write over Modbus to an Arduino, and then I've actually written click code that does the incrementing that I was showing you in the Modbus in this example. That actually connects over Ethernet, Modbus TCP to the Arduino, and every half a second when it increments the counter, it sends that counter to the 7 segment on the Arduino. I could also be reading the numbers off of the Arduino, the sliders, and sending them to something in here, but I haven't built that yet. I think that's enough about Modbus. So I walked through that example. Question?
Yes.
Yes.
So it's over TCP/IP. How complicated a network can it deal with? Like any normal Ethernet, TCP/IP network, or is it limited to a single VLAN?
I'm not you.
Okay.
So I don't have an answer for this.
Okay, that's a fair answer.
The Allen Bradley Rockwell is the big automation company for America. And they sell managed switches, like Cisco switches, to go in your rack that probably do all sorts of crazy stuff with that. They have like a time synchronized communication protocol that is not Modbus. They use a different protocol that I'll mention in my next slide, actually. So there certainly are people doing network shenanigans, but I'm not working at that level. I tend to have an isolated thing, which is why I chose 172 whatever, because it tends to not be the address of the rest of the network I'm dealing with. So when I have my laptop, it's not unsure about where is my PLC, which network is it on, whereas if my PLC and my local network are 192.168, it might. So actually, there are more protocols, and I am not going to spend multiple nights talking about all of them. In the Allen Bradley world, they have one called Ethernet IP. And I'm facepalming here because that is a very, very ambiguous name. What does that mean? It is built on top of Ethernet and IP, and it's a communication protocol where one device talks to another repeatedly and receives messages, and it will do this at a high frequency. And there's a structure to these messages that defines like the message size and whatever. It's a communication protocol. What's really cool when you're doing automation in the Allen Bradley world with Ethernet IP is you will get a XML file from whatever vendor you're buying a thing from that you're integrating with that defines the message structure, that has all the variable names and types defined. So you'll say, I'm connecting to a new thing. The new thing is the servo drive. You load the XML file for the servo drive, and suddenly all of the variables communicating in both directions are already defined. Unfortunately, if you're not in the Allen Bradley world, that XML file might not be the one that works for the PLC you're working with. So that does save you a lot of trouble over reading data sheets in the Modbus example. And then others of these are other protocols for other similar kind of things. EtherCAT is very common for connecting multiple devices together in a high frequency way. There are EtherCAT IOs. I'm not going to go more into that. Circos and whatever names. You're going to see the names. I want to go back to programming though, because ladder logic is not the way I expect people familiar with Arduino to do things. And unfortunately, I can't get my demos working. But I can go through my slides and I can show you code. So let's go back to the slides I skipped. Yeah. I like typing code in. I don't think ladder. I don't think boxes that feed a thing that increments a number. Actually, this incrementing a number thing is super helpful in the click. You can type math in here and like just have a box that does math. I want it to divide by 2 and add 7. Just type it in. You don't need to have multiple functions for it. Where other ladder logic PLCs, that may be multiple rungs. But I like typing my code in with semicolons. So I work with structured text. We have a question here at the iPad.
We do. Does each Modbus TCP device have a separate address, or can you put a bunch of them on one IP on different ports?
When you configure your Modbus communication, you configure which network adapter it will do that communication on. So in the click, when you configure, I've already forgotten where it is. COM port setup. There are multiple communication ports on the click. There's the Ethernet and the RS-485 and Wi-Fi, and you can configure a different Modbus device that you're talking to at the same IP address on Wi-Fi as you would on Ethernet. Most PLCs, however, don't have more than maybe 3 Ethernet adapters, so you wouldn't typically be doing that. So structured text works very similar to what you're used to with Arduino. The syntax is a bit different. Assignment is : equals. Variable declaration still has a type and an initial assignment. You can declare arrays. Arrays are pretty cool. You can specify the indices of the array. So if you want it to start at 1 because you're not a C programmer, you can make it start at 1. You can make it start at 1,000. You can do multi-dimensional arrays. You can look up how to do that. You can do pointers. I expect you're typically not going to be doing pointers because you're typically not going to be doing dynamic allocation, but you can. You can do if, else. You can do for loops. You can do while loops. Statements end in semicolons, double slashes or slash star, multi-line comments like you're used to. Switch case is a little bit different. Break doesn't fall, case doesn't fall through to the next case by default. There still is a break statement for jumping out of loops. It is exit. There is still return and calling functions. You can define structures with types and fields. You can define enumerations, and they're fine. Let's look at what my structured text demos are. Where did I close the PLC? No. So this is our trivial counter increment and setting the orange lamp to the logic we had previously from the ladder logic. Instead of the double ampersand or double pipes for and or, they are and or. A thing I want to mention about the PLC IDE is like we saw in the click when we were connected in debugging, where it was showing the variables of the running code. this button right here, activate live debug mode. Okay. Right here, does the same thing in this IDE, and commercial PLCs, their other software tends to have the same feature. What was the next demo I wanted to show you? Yeah, so I showed you the counter. Let's talk about program organization. So you can have functions. So I already showed you building another function to run in the multiple tasks. But what if you have, but if you want to define a thing to that you want to reuse in your code, so you've got some special kind of delay, or you have an actuator that has some logic and you have multiple of these actuators and you want to replicate the logic for the actuator. Or if you want to program in some other language. This is called a function block diagram. So this is the same ladder, the same start and stop. No, this is blink. I didn't show you blink. Okay, let me show you blink. So I wanted to do blink a light, and oh, maybe I did show you blink. So I had the sorry about the jumping around my brain. I want to show you blink. Opta PLC ladder blink. So we have we're feeding the output back to itself through 2 delays to blink a light. So this blink out I've mapped to a pin, but it could be a relay, and the output we're again using as an input but inverted, and then feeding it through 2 of these delays. So this is a turn off delay, and the delay duration is 250 milliseconds, and then this is a turn on delay. So when it changes, the change starts propagating through the rung immediately, but it gets delayed by the delays before it takes effect. So it's not toggling the output as quickly as it possibly can. So this same example could be done as more of a electrical schematic and not ladder logic schematic that you can then reuse as a function in another part of your program, is the example I'm showing you here. So this is the same. I bring the LED out back in through a separate input variable, which I invert, and then I feed that through a turn on delay and then a turn off delay and feed that to out. So this function block here has a var input of the LED in and a var output of the LED out. But this could be written as structured text as well, or ladder. And then I'm calling this from main. So in main, I have an instance of the function block, and I call it with the in variable mapped to the LED pin, and then I assign to the LED pin the output of the function block. So here's where I execute it, and here's where I read the outputs from it. I have a question.
Does each Modbus TCP device have a separate IP address, or can you put a branch of them on one IP on different? Oh, I did. I'm sorry. Okay. Second one is, this feels a lot like Pascal.
Sure. Sure. Yeah, the colon equals assignment is what Pascal does. Another thing I forgot to mention is that when you create a new project, like file new project, there's a prompt there that asks you if the variables are case sensitive or not. So typically they're not case sensitive, but they optionally can be. So so the creating structure with function with inputs and outputs can be done with ladder or structure text or the function block diagram, which I showed you with the wires. And then those have inputs and outputs, and you can instantiate more than one of them. And then when you're debugging, you can actually click into the function block diagram, and right here it will let you choose which of the instances of that to show the variables of. So you can have multiple of these and debug just one of them by doing that. I think that's the most complicated code I'm going to show you here today. Actually, that is the most complicated anything I'm going to show you here today, because that's the last slide I haven't showed you until I start talking about other PLCs. So yeah, I brought some other things in today. This weird guy is PLC with an Arduino for a CPU. So the CPU module here is SAMD21 Cortex-M0 that you program from Arduino, not from the PLC IDE. And then there's shields that snap onto one side, and then PLC IOs that snap onto the other side. So this from Automation Direct is the P1AM100. They have a similar one that's Cortex-M4 that's slightly more expensive. So much like I was doing earlier with the quick I2C cable to the OLED and the light sensor, this will run exactly the same code plugged into the shield here. And I can also talk Ethernet TCP or, Modbus TCP or Modbus RS485 with modules that plug onto it. And then this one module here just breaks out all of the remaining pins. So these pins are 3.3 volt logic because they go straight into the CPU. And then the IOs snap into the side and have their own little controller inside that talk to another controller on this board inside. Internally, it actually talks SPI from the M0 to an STM32, and then that talks down the IOs. And then this is another PLC I bought for work. This module here, the CPU, is about $400, and you can program it in structured text or ladder or the other languages. What's really cool about their software, sorry, this is from LG, sorry, I forget who it's from, LS Electric on Automation Direct. It's called the XGB. The CPU is about $400, but a reason you might play with it without potentially buying one is you can download the free software, and they have a simulator in the software that you can run on your PC. The reason I purchased this one is because the CPU has 6 axes of step and direction, and then for $400 you can buy an EtherCAT master for doing motion control. You might buy a PLC from Allen Bradley, Rockwell, Automation. They have a huge variety of stuff, and they're the most popular in America for this kind of thing. But they're all ladder logic, and that's not the way I think. Yeah, we have another question?
We do. So why use these modules instead of, say, a Raspberry Pi and some relays, shields, etc.?
So yeah, there's a bunch of features that are represented by the physical build of these devices that don't line up with the way that having an Arduino in your panel or a Raspberry Pi or whatever else does. For example, the click, when we were connecting to it, it was telling me the project saved in the PLC. I can save the code in the PLC as well. So if I'm working on like plant automation stuff, I can save the code in the PLC in addition to my file server so that the next technician will definitely have my code. But if I'm shipping a product, I can turn that off, saving the code in the PLC, because I don't want like the technician on the product site working on my screw compressor or whatever to connect and change the code inside of my screw compressor or my hydraulic press PLC or whatever. Additionally, they are built to withstand vibration and higher temperatures. So typical cabinet ratings, I think, are 85 Celsius, and there's some vibration G-force rating. And they're also meant for like in-circuit, cabinet installation and maintenance and replacement. So the Click, for example, has all of the connections on terminal blocks that unplug. So if I blow up this module, I can pull it off, put another one in, and then connect my entire set of connections at once. Whereas some other PLCs like the Opta have screw terminals where you need to mess with the individual wire. Sorry, Opta's over here. Mess with the individual wires. So more built for reducing downtime. Is there more to that question I didn't answer? Okay, yeah. You're definitely paying more for robustness and some options for alleviating problems with whatever, continuous operation, as the technicians working on the devices aren't the same technicians. Yeah, I described to you how PLC ladder logic is derived from relay logic and what that looks like, and how it's not your only programming option for PLCs. If you pay attention to what PLC you're purchasing, you can program it in structured text, which works very similar to what you're used to in Arduino, with the same kind of control flow and structure, but you can map variables to inputs and other devices to expand your communication. And as your integration of things gets larger and larger, because you might have, a 200-meter long factory line with sensors all the way down it for all sorts of stuff, there's options for you to expand there that aren't as straightforward as just putting the same thing on top of your Arduino and expecting it to run. Any more questions?
I'm kind of expanding on my previous question, but could you have other normal TCP/IP devices on your same network? Yes? Okay, easy enough.
When choosing one of these, do you take into consideration the ease of programming, the ease of setup? And if so, are there PLCs now that work toward easier programming languages, like Python or LabVIEW?
I don't consider LabVIEW an easier programming language. Yes, there are definitely PLCs that you can program in Python. They don't have the same control options. So the Rexroth Control-X core that I use at work is a dual-core ARM64 Linux PC, similar to Raspberry Pi 4, but it has 3 network interfaces and motion control for 10 axes and whatever. It costs like about $3,000 when you get licenses into it, list price. One of those licenses is a thing to install a Python IDE that you run in a browser to program on it. And you can talk to the motion control or your IOs that you plug in from that. There's a number of different software that you can use with that. And I didn't want to mention it today because I'm not quite sure exactly how approachable getting that software is on your PC to run. But when you sign up with a Bosch Rexroth ID, you can go download the programming software onto your PC, and they run a VM with a virtual one of those devices with all of the licenses unlocked, so you can install all of the software and run it virtually on your PC. The limitations they put on that is obviously you can't do motion from your virtual PLC. You can do virtual motion, but not like control a real servo drive or IOs or whatever. And the virtual engineering license can only have 4 hours of runtime before you need to reboot it, and then it'll run for another 4 hours, which for development and testing isn't really a problem. And that means that you can start one of the reasons there and other vendors are pitching the simulation and virtual devices is so you can start developing your PLC code before your hardware and your control panel is even built. Another example of Python is this guy, the P1AM. The P1AM 200 you can program in CircuitPython. Have you worked with CircuitPython before? Yeah, so to explain to everyone else, CircuitPython is another embedded programming option for these where you plug in the device and it shows up as a drive and you edit your main.py or your other py files, and when you save them, it reloads them and starts running your changed code in the controller itself.
Are there any JavaScript PLCs?
Would you like to repeat the question?
Oh, God. Are there any JavaScript PLCs?
Thankfully, none come to mind. Although going back to the Rexroth one, another option for that is Node-RED. And the Click will talk MQTT, for example, so you could integrate the two that way. Cool. That looks like all the questions. This has been fun. Sorry about the demo gods.
Significantly more work than I think the last.
Murphy was here today. Anyway, I'll try to get the code and the slides onto GitHub tomorrow.